Good morning, everyone. So yesterday we reviewed doing rates of change and kind of talking about them graphically, what a secant line is, what a tangent line is, how to draw a tangent line, and get instantaneous rate of change that way. Okay, so in advanced functions, you also would look at how to do that algebraically, right, using the equations. So that's what we're going to kind of be reviewing today and extending that a little bit. So we're going to start off right with an example and bring this out of advanced functions here. Okay, so the equation of an object falling from the top of the CN tower, right, there's the CN tower again, okay, is S of t is 555 minus 4.9t squared, where S is the height above the ground and t is the time in seconds. So we're going to figure out the average rate of change for the first 5 seconds and the instantaneous rate of change for 5 seconds. Okay, so hopefully from advanced functions, you remember how the formula works for instantaneous rate of change. Okay, so the way I calculate my instantaneous rate of change, right, I want my change in S over my change in time. So the way I'm going to do that, I want over the first 5 seconds. So that means this is from the interval between 0 and 5. Right? It's not a vector, that's an interval there. Okay, so that means I need to calculate what is S of 5, okay, minus S of 0, okay, divided by 5 minus 0, right? Function values at my endpoints divided by the change in the x values there. Okay, so let's run each thing through. So for S of 5, I got 432.5. For S of 0, that would be 555. This is all going to be divided by 5. So when we work that through, I got negative 24.5. Again, the units on this was going to be meters per second. Okay, so the average rate of change over the first 5 seconds was it was dropping at a speed of negative 24.5 meters per second. Or I should say dropping at 24.5. Okay, now for instantaneous rate of change. And again, you would have encountered this situation, hopefully in advanced functions. Okay, if we try to do the same idea as what I have here, okay, well, I want the change in S or the change in time. Okay, well, what's my interval? Well, I only have 5. Okay, I don't really have an interval. Okay, so depending who taught you this course, there's 2 approaches you may have taken to this. Okay, so I'm going to briefly outline each one before getting into calculations. So the first one might have been to do a little interval around that time. So an interval around 5. Okay, so maybe I'm going to pick something really tiny. I'm going to go from 4.99 to 5.01. Okay, and my calculation would be S. So S of 5.01, okay, minus S of 4.99 divided by 5.01 minus 4.99. So we just do a really, really tiny interval around that and say that's probably going to be pretty close to what the tangent line is. So in this case, if we run that through, negative 49 meters per second. Okay, and that's nice and accurate. And I believe to check it for consistency, right, we might do an even smaller interval. So maybe I do this again. Maybe I do between, whoops. Okay, maybe I do that between 4.999 and 5.001. Okay, just to make sure that it's doing what I think it does, we do it on a smaller interval and check. Okay, that's one technique you can use. Okay, another technique, again, it depends who taught it to you, is to only change one end of the interval. Okay, so for instance, maybe I leave the 5 alone. So this is kind of method 2 here. Okay, and the way I'm going to do this is I leave this end alone, 5, and I just make a little interval above it. So 5.01. Okay, so my calculation this time would be, oh, there we go again, would be S of 5.01 minus S of 5 over 5.01 minus 5. And I apologize for my sloppy writing. It's making all those S's and 5's look exactly the same. So when I ran through this time, I got negative 49.049. So rounding it off, it's essentially the same thing, negative 49 meters per second. And again, the idea with this, to make it more accurate, would be now make it a smaller interval. Maybe I use this again with 5.001. Do it again with 5.0001. See what happens. In this case, you're just going to get more zeros in the middle there, and it comes down to 49 meters per second. So the reason this works, okay, is because you're just taking an interval and getting closer to that tangent line. So I'm just going to show you in Desmos kind of the idea here again. If this is my function, okay, so k is kind of that extra little bit that I have there. So as I make that little bit smaller, right, I get that I'm closing in. So when I'm only one away, 0.8, 0.6, 0.5, 0.4, okay, that line is moving closer and closer to being the true tangent line. Okay, if I zoom in, right, I'm not quite there yet. It's still not perfectly flat, but it's getting closer and closer and closer. So by closing that interval, I'm making the slope closer and closer to the tangent line. So now we're going to try to formalize that procedure algebraically. Okay, so here's the basic idea of how it would work. And we're just going to use an example here. Okay, so for x squared, we're going to simplify what we call a difference quotient, and then figure out what the slope of the tangent line is at x equals 1. Okay. So what I mean by a difference quotient, and actually we'll maybe just kind of put these right together and do it as one piece. Okay, and maybe we can do it more generally. So the idea is when I'm setting this up, if I do that even interval, okay, I want to know at 1, okay, the interval between 1 and a little bit more than 1, right? You start at 1.1 and then 1.01. So I'm going to model that as this 1 plus, I don't know, let's call that h. Okay, so I'm doing an interval from 1 and a little bit more than 1. So I start the procedure the way I normally would. Okay, if I want the change in my function, so change in f of x over the change in x. Okay, the way we run that through is I say, well, I want f of my endpoints, so 1 plus h, minus f of 1 over, okay, I have 1 plus h, multiplying 1. Okay, right? Function at y2, function at y1, y2 minus y1. Same thing as your slope formula. Okay, now my function was x squared, so that means I have 1 plus h squared minus 1 squared over, and if I tally up this denominator, I have 1 plus h, then take away 1, so I've really just got h. Now let's do some expanding. So that 1 plus h squared, and this is where the algebra stuff gets really important, right? So I'm going to get this on the side because it came up on the feature midterm a bit, right? If I have 1 plus h squared, that means I'm doing 1 plus h times 1 plus h, and now I have to distribute that out. Okay, so when I distribute that out, the terms I'm going to get are 1 squared, so 1. Okay, 1 plus 1 times h, and another 1 times h, and another one of those is plus 2h. Okay, and then plus h squared, and then take away 1. That's all divided by h. Now do some tidying up. The ones will cancel out. So I have 2h plus h squared over h. Okay, every single term has an h, so I can divide everything by h on the bottom there, and we're going to have 2 plus h. Now, you might be wondering, how does it really help you? Still got h there. Okay, but remember what we were trying to do. Okay, the idea was that that h represents a really small value that we were going to make smaller and smaller and smaller anyway. So we're essentially trying to bring it to 0. Okay, right? Ideally, I would want h to be 0, because then I'd have my tangent line, 1, 1, at the same point. Well, if I put in h for 0 here, what happens? Right? I've got 2 plus 0, so my rate of change is 2, and that's it. I'm done. Okay? So that's the idea of just taking this process and making it more general with algebra, right? You don't have to test 3 different sets of intervals. Okay, I can set it up generally with algebra, and this shows me what my rate of change will be. Okay, so for our final example, we're just going to try that again with the original problem we had. So I was trying to find the instantaneous rate of change, right? So my change in s of t with my change in t. Okay, so that's going to be, and it was at 5, I think it was at 5, right? So I want s of 5 plus h, some little amount, minus s of 5 over 5 plus h, take away 5. Okay, what was my function? My function was 555 minus 4.9 t squared. Now my t here is 5 plus h, okay, minus, and I'm going to put some square brackets here because I have a lot of stuff to write in here. Okay, I have 555 minus 4.9 times 5. Okay, and again, in my denominator, those 5's cancel out nicely, and I'm left with h. Okay, and I think I forgot something there. These were squared, t squared, t squared. Okay, in the numerator, I have some expanding to do. So, and I have some canceling I can do. I have 555 minus 555. So I have negative 4.9. Okay, inside the brackets. Okay, I have to double that and FOIL it out. So I have 25 plus 10h squared. Sorry, not squared. 10h plus h squared. And in the end here, I've got double negative, so plus 4.9 times 25 when I square that 5. And it's still all divided by h. All right, so 4.9 times 25. So I have negative 122.5 minus 4.9, 49h minus 4.9 x squared plus 122.5 all over h. Okay, tidy up step. Well, my 122.5s cancel out. I can divide what's left over by h. So I have negative 49 minus 4.9 h. Okay, and now our last thought, like before, is that, well, the idea was this value of h is going to get smaller and smaller and smaller. It's going to get closer to 0. So essentially now I can say, well, that's going to be negative 49 minus 4.9 times 0. And oh, look, I got negative 49. And that's the rate of change that we got when we did it using the intervals. Okay, same value. So again, that's the basic principle, okay, is instead of having to just do the manual calculations over and over again, if I set up this thing called a difference quotient, right, this is my target value, I want it to be at 5, and I'm just adding a little bit on one end of that interval, and I do some algebra, I get down to an expression where I can get rid of the h eventually, and I know exactly what that rate of change will be. Okay, so that's how you use the difference quotient to simplify an expression and determine your instantaneous rate of change. Okay. So for practice work, okay, there are some questions to do for practice. Okay, thanks very much for watching. I hope you enjoy your 3-day weekend, and Monday we'll have some time to clarify anything from the past 2 days and keep on rolling along. Okay, so again, have a nice weekend, and I will see you on Monday.